Good afternoon, everyone. I am Oleg Pursky from State University of Trade and Economics. Dear colleague, let me present to your attention the result of our research on the topic laboratory equipment for practice learning in the framework of educational course Molecular Physics and Thermodynamics. In physics education, an extremely important factor that determines the learning quality is the process of forming students' practical skills through experimental research. The performing laboratory work, students learn to use physical device as a means of experimental research, which together with theoretical learning provides a basis for a full understanding of physical process or phenomena. An important stage in the development of intellectual education scientific abilities of students is not only the study of theory but also the implementation of the theory in practical activities. Therefore, modern methods of teaching physics foresee the involvement of students in such types of educational activities that allows to use the acquired theoretical knowledge in the practice, in particular to perform laboratory work by students. The modern course of molecular physics and thermodynamics present rather complex theories that require experimental verification for a better understanding by students, in particular transfer process and kinetic phenomenon in liquids, phase transition, isobaric and isochoric, adiabatic, and other thermophysical processes. In this study, we present developed laboratory equipment for practical training, in particular experimental research of temperature dependence of heat transfer process in molecular liquids under isobaric condition, and described the procedure of for its use. Uh, Temperature dependence of thermal conductivity are investigated as a rule along isobars and isochores. At the same time, it should be noted that various experimental methods were used to measure thermal conductivity coefficient, in particular linear flow state method and radial flow steady state method. The stationary methods are simpler and more reliable since they are based on direct measurement of thermal conductivity. One general conclusion can be drawn from the considered experimental method of measuring thermal conductivity coefficient. No of existing method of measuring thermal conductivity can ensure 100% distribution the controlled heat flow through the sample, only due to its thermal conductivity. There are always processes that affect the measured values of thermal conductivity coefficient, thus introducing significant error in its value. Therefore, when choosing one or another measured method, it is necessary to take into account the specific of scientific task, take into account the temperature range of the study, the pressure range, and the characteristics of the substance under investigation. The study to study the isobaric thermal conductivity of liquids among the stationary experimental method, the most successful constructive solution from the point of view of minimizing the influence of additional factor on the process of measuring thermal conductivity coefficient is the radial flow steady state method with the coaxial geometry of measuring cell. The peculiarities of the thermal conductivity measuring method for liquid put specific requirements both on conducting the experiment and on the measuring equipment itself. For this purpose, laboratory equipment was created for measuring isobaric thermal conductivity of liquids. The general decision scheme of the installation is shown in Figure 1. The created experimental technique uses general decision solution of the coaxial cylinder method, preserving its features and measurement precision in general. The installation allows measuring the coefficient of thermal conductivity of liquids under atmospheric pressure and saturated vapor pressure in the temperature range from 115 to 400 kelvins. Cooling to below room temperature is carried out to the use of removable cooling conductor, see figure 1a. When placing the cooling conductor in the transport drum, its lower part is in contact with the liquid nitrogen. The measuring cell construction is shown in figure 2. It consists of two coaxial geometry cylinders between which the liquid under study is located. The measurement cell was produced from the Cooper. Along the axis of cylinder 1, a hole is drilled or pressed in zinc-welded tube 2 made of stainless steel. The liquid samples vary between outer one and inner three cylinders. Liquid have small thermal conductivity coefficient 2 or 3 order lower than the thermal conductivity of metals. With such construction of measuring cell, the thermal resistance of the metal layer of the inner cylinder 3, which occurs between the liquid and the internal thermometer 7, and the boundary capacity thermal resistance on the outer one and inner three cylinders. In comparison with the thermal resistance of the liquid, sample layer can be ignored. The use of one thermometer during temperature gradient measurement made it possible to avoid the influence of unaccounted heat flow and the difference in the calibration of thermometer on the value of thermal conductivity coefficient. With this method of measuring thermal conductivity, the maximum possible error in thermal conductivity values associated with unaccounted power losses of the interval here turbine due to thermal radiation does not exceed 0.2%, with a temperature gradient of no more than 0.5 Kelvin. The reliability of laboratory installation was determined from a series of preliminary experiments on measuring the thermal conductivity of exemplary liquids. None, toluene, and ethyl alcohol were chosen as the template liquids which were studied in data. The main factors that depend on the correctness of the thermal conductivity coefficient measurement by the radial steady state method are occurrence of the temperature gradient determining and stability of the measuring cell temperature during the experiment. In this installation, platinum resistant thermometer with sensitivity to temperature change 0.0005 Kelvin are used to measure temperature and temperature gradient. The accuracy of maintaining a constant temperature of measuring cell is no worse than 0.005 Kelvin device hour. The measurement error of liquid's thermal conductivity coefficient does not exceed 3%. With the help of created laboratory installation, it is also possible to measure thermal conductivity coefficient in the temperature areas that correspond to pre-crystallization temperatures. The thermal conductivity coefficient calculated using Formula 1, the parameter and their characteristic. The parameter that included in Formula 1 and the characteristic presented on this slide. On this slide, you can see temperature dependence of platinum-resistant thermometer that used in calculation of thermal conductivity coefficient. Developed laboratory equipment has certain features and advantages compared to prototype. Firstly, it is a wide range of temperature for measuring thermal conductivity. And secondly, it is compactness and economy in the use of the investigated substance and coolant, liquid nitrogen. The main features of developed equipment is the cooling mechanism of the cryostat by immersing its lower part in the transport reservoir with the liquid nitrogen. Such a cooling mechanism provides a significant saving of cryoliquid and allows obtain a constant temperature of the cryostat external environment in a fairly simple way, which is an important factor in stationary method of measuring thermal conductivity, in particular in the procedure of stabilizing the measuring cell temperature. Conclusion. Measuring the thermal conductivity of molecular liquids is associated with a number of difficulties, among which the following can be highlighted. Ensuring the measurement process in the low temperature range, ensuring free expansion of the liquid inside the measuring ampoule when the temperature increases, minimization of health losses due to higher radiation, and uncontrolled heat flows, ensuring the necessary accuracy of measurements. The present laboratory equipment for measuring isobaric thermal conductivity of molecular liquids allows positively solve the mentioned problem. The use of measurement of the thermal potentiometer method allows to avoid the error arising in the values of the thermal conductivity coefficient due to uncontrolled heat flow and different calibration of thermometer, and significantly increases the measurement accuracy. The created equipment for measuring thermal conductivity of liquid by stationary method of radial heat flow allows, due to the specific of measurement techniques and the construction features of the measurement cell of coaxial geometry, to avoid convective heat transfer. The presented laboratory equipment will be useful for forming practical skill for physics specialty students. Thank you for your attention.